Swayam Prabha. Digital India. Educated India.
Let us now talk about interrupts and exceptions. So these are very important features in modern pipeline processors, and they are required particularly while interacting with I/O devices. For our I/O devices, input-output devices like the keyboard, the mouse. Alright, so what happens when you press a key? So if when you press a key on keyboard, this is the precise sequence of actions. So what happens is that the keyboard first logs the key press, right? So every time we press a single key, the keyboard records which key was pressed. It converts the key to its equivalent ASCII code, which is a 7-bit number, or its equivalent Unicode code, which can be a multi-byte number. It depends on the language, right? So this is this step. Then it sends the code of the key that was pressed to the processor. So once this is sent to the processor, what the processor receives is an interrupt, right? It is receiving an interrupt. An interrupt is a certain message which can appear anytime, like you can press a key anytime. So the keyboard sends an interrupt to the processor, which is essentially a single bit signal that, look, there is some data arriving. It's like a doorbell. You can think of an interrupt like a doorbell, where the keyboard pretty much rings the bell and tells the processor that there is a message waiting for it. And then what the processor does, so at that point, either the processor is idle or it is running a program. If the processor is running a program, it suspends the execution of the current program, it stops it. And then it jumps to a specialized program, another program, which is within the operating system, right? So operating system is basically a set of specialized programs to manage normal programs as well as the devices connected to the computer, such as the mouse and the keyboard. So once we receive an interrupt, we jump to the interrupt handler, which is a very small program which is meant to process the input. So the interrupt handler will then, so if I press a key, then the key is coming on the screen, right? So its job is to invoke, either do it itself or invoke another program, is a separate issue, but essentially draw the shape associated with the key on the screen. So for example, if we click the O button, then what is drawn on the screen is pretty much an O, right? So what if I, let's say, press O at a certain point, then an O is drawn. If I press K, then a K is drawn. Similarly, I can receive an interrupt from the mouse or from the tablet that I'm using. So my tablet is saying that the pen has moved, let's say, 1 centimeter to the right. So what the processor is doing is that it is running the interrupt handler program, which is moving the dot that you're seeing on the screen 1 centimeter to the right, and also drawing a line in this case. So after the interrupt has been processed, which means that once the value of the letter that was pressed on the keyboard that comes on the screen, or let's say the mouse pointer moves, the processor returns to execute the original program that it was executing right before the interrupt. So the way we can visualize it, that a program is executing, then an interrupt comes, the interrupt handler is executed, then again the program starts, again the interrupt handler executes. So that's the way it continues. Alright, so this is interrupts. So then there is a term called exceptions. So exceptions are generated when a program accesses an illegal, it can be generated in many situations, but pretty much it's a situation which is not normal. It's an exceptional situation. So one way can be when a program accesses an illegal address, right? When the address itself is not legal, right? So, some sort of an address which is if this is the address space that we are allowed to use, some sort of an invalid address right? If the program accesses that, then it's a cause of an exception. Or if we divide, 5 divided by 0 and it's an integer division, the result is infinity. But infinity does not have a representation in integers. So that's also an exceptional case. Or if you issue an invalid instruction, an invalid opcode, that's also an exceptional case. So we can have many such exceptions in this fashion, where uh, essentially the program does something which is not right, not correct, not in the normal course of actions. And this is an exception. So exceptions are handled the same way as interrupts. So interrupts have an interrupt handler, exceptions have an exception handler. So if you access an illegal address, then the exception handler might just terminate the program and let the user know that an illegal address has been accessed. So once the interrupt and exception handler execute, after that we come back and start executing programs. Might be the same program that was executing before the interrupt or exception, or might be another program. Alright, so the most important property in this lecture that we want to define is something called precise exceptions. So we'll give an informal definition first, and then we'll give a formal definition of precise exceptions. So the informal definition is that we need to return to the original program at exactly the same point at which we had left it. So let's assume that in the original program we had executed some instructions and then an interrupt came. So when we go back, we'll pretty much have to start from exactly the same point at which we had left, right? So we can't skip an instruction, neither can we execute an instruction twice. So what it is saying is that the execution of the interrupt handler, so we'll use the terms interrupt handler and exception handler interchangeably. So in this case, interrupt handler means both interrupt as well as exception handler. So the meaning has to be inferred from the context. So what we are saying is that the execution of the interrupt handler should not disrupt the execution of the original program in any way. So what we mean by the fact that the execution is not disrupted in any way, it basically means that the outcome of the original program should be independent of the fact that there was an interrupt, right? Unless it is dependent on the interrupt, right? The interrupt is unrelated to the program, then the outcome of the program, the final output or any of the outputs of the program or the behavior of the program should be absolutely independent of the interrupt, right? Unless, of course, it's dependent on the interrupt. For example, if the interrupt is an exception, so then something like if you do 5 by 0, then of course some then in some systems the program may be terminated. Then of course it is dependent. But let's assume that in this case the interrupt or the exception, whatever it may be, is not related to the program. It's not an exception. It's just a key press. Then the execution of the interrupt handler or the interrupt handlers should not disrupt the execution of the program in any way. So the output of the program will remain the same, right? The final output, the outcome of the program will remain the same, and there should be no disruption whatsoever, right? So the same instructions will execute. So we need to ensure that this happens, right? The process of interrupt processing is seamless. Otherwise, what will happen is, let's assume that I am playing a chess game, and after that in the middle I click some buttons, or let's say open another program and do something. So then the moves of my chess game will change, but that does not happen. The reason that does not happen is because we have some notion of a precise exception. So note that a precise exception, a precise interrupt is the same. So the word exception and interrupt are used interchangeably. And the reason that that does not happen is basically because we ensure that when a program executes, it executes completely on its own. If an interrupt comes and the interrupt is not related to the program, then we process the interrupt. So we execute the interrupt handler, and then the original program starts. The original program otherwise is oblivious of the fact that it was interrupted in the middle. So let's now have a slightly more formal definition. So let us consider the sequence of dynamic instructions in the program as I1 to In. Let us further assume that an instruction completes after it either updates memory, writes to registers, or reaches the MA stage, which in this case, which means that something has happened. And what has happened? Well, let's see. So if for the CMP instruction, the flags register would have been updated. For B, BEQ, BGT, and RET, the the value of the new PC would have been written to the PC register. Right? So let us define a notion of completeness of an instruction once again. An instruction completes if, let's say, either after it updates memory, or writes to the registers, or reaches the MA stage, whichever is earlier. Right? And so basically for the branch instructions, by the MA stage would have updated the program counter. The compare instruction would have updated the flags register. So basically that's how we define a broad notion of completeness. So which means that some notion to permanent state would have, some change to permanent state or permanent registers would have happened. So for example, if an instruction has written to memory, right, we say that it is complete because its job is deemed to have been done. Similarly, if an instruction has written to a register, we say it is done, or it has written to the flags or updated the PC, we say that it has done. So let the last program instruction that completes before the first instruction in the interrupt handler completes, let it be IK. Alright? So the reason that we are defining so much is basically because in a pipeline there will be multiple instructions, right? At one point. If this is a pipeline, we will have 5 instructions at the same time. Let's assume that at this point the interrupt arrives. So what do we do? So let's say if the interrupt arrives, if we kill all of these instructions, that will be wrong. Because the instruction in the maybe RW stage is maybe a store instruction which is already completed in the MA stage. So if we remove all of this and then later on start from this instruction, it will be wrong because we'll be redoing work. So we don't want to do that. So that's the reason we have to be slightly more careful when we define the notion of instruction completeness, and also how we ensure that we stop an already executing program very carefully, execute the interrupt handler and again come back, right? So this entire process has to be done pretty carefully. So that's the reason we define one additional terminology, which is instruction IK, which is the last instruction in the program that completes before the first instruction in the interrupt handler completes. So let all the program instructions that complete before the first instruction in the interrupt handler completes be represented by the set C. So what we want is that for an outsider, he will see that all the instructions in the set C have completed, and then the interrupt handler executes. It executes in totality, and then the execution starts. So the last instruction to complete here is IK. So then the execution starts from IK plus 1. So recall that in some situations we might want to execute IK once again. We will discuss when are those situations in chapter 10, but right now you need to take my word for it. But in general, if we have done till IK, we can start here from IK plus 1. So the formal correctness condition or the formal correctness criteria that we want to define is that if any ij is element of C, which is a set of instructions that have completed before the first instruction of the interrupt handler, then j is less than equal to k, which means that ik in program order is the last instruction to complete. All other instructions that are a part of C complete, So recall that C was declared here, that C was declared here as the set of all instructions that complete before the interrupt handler. So if any instruction ij is a part of C, then this implies that j is less than k, less than equal to k, which means that it's one of the instructions before it. And no instruction after ik will actually complete. So we need to ensure this condition. In addition, we need to ensure one more condition, that no instruction of the form ik dash, where k dash is greater than k, should complete before all the instructions in the interrupt handler complete, right? So if you consider ik and if you consider ik plus 1, so between them all the instructions in the interrupt handler have to complete, right? They have to completely finish, and only then will we start executing instruction ik plus 1. Alright? Then after returning, we can seamlessly execute ik, either the same instruction in some cases, especially when the execution of ik was not correct, so it's required to execute it once again, or we need to execute ik plus 1, which is the next instruction. So this is something like we are trying to ensure that the execution of the interrupt handler is completely invisible. It somehow happened in the middle, it finished its job and went out. We were not able to know. And this problem is particularly difficult. Had it been a single cycle processor, this would have been very easy. That once the interrupt comes, we finish the execution of the current instruction, that becomes ik, and all the instructions before it, which is the set C, have already completed, and then we execute the interrupt handler and then we restart. But since it's a pipelined processor, right, with 5 stages, 1, 2, 3, 4 and 5, if an interrupt comes, it'll become it's slightly difficult. The reason it is slightly difficult is because some of these instructions, maybe this one or this one or this one, some of these instructions might have made some changes to the permanent state, so they should be allowed to complete. And some of these instructions might not have made any changes to the permanent state. So then maybe the instruction in the fetch stage can be discarded, the instruction in decode stage can be discarded, and for the rest we need to see. So it's like that we need to ensure that the instructions that have at least made some progress need to complete, and some which have not, they can be discarded because they have not updated any state. So this is required to ensure both these conditions, that before ik all the instructions have completed, after it none have completed, and also when we finish, it also says that once the interrupt handler starts, it needs to complete all of its instructions, and no instruction of the form ik dash, where k dash is greater than k, some instruction after ik should complete before all the instructions in the interrupt handler complete. Alright, so that's the broad precise definition. It is the same as the informal definition, means that the interrupt handler's execution should be in a sense informal. And so we can clearly see that if we don't follow this precisely, a lot of problems can happen. Consider a branch statement. So if the branch statement, we allow it to update the program counter with a new value, right? So instead of 10, the offset, we make it 20, and we somehow end up executing the same branch statement once again, and let's say the offset in the branch statement is 12, it will again add 20 plus 12 and make it 32, which will essentially add the offset twice. So you have to ensure that one instruction does not execute twice unless we want it to. So what we do, the way to do it is that when an interrupt arrives, we mark the instruction in the MA stage, because all the changes are being made in the MA stage. Even a branch instruction is making the changes in the MA stage. So so this marking the instruction, we will if there's only if an interrupt arrives, then only we'll mark it in the MA stage. We'll mark whatever instruction is there in the MA stage. Otherwise, if there is an exception, we mark the instruction as soon as it encounters a fault or exception, and this instruction can be in any stage. So for example, in the fetch stage, if there is an exception, we'll mark the instruction in the fetch stage, right? So whichever stage causes an exception, or if we have a divide by 0 like 5 by 0, and the EX stage it causes an exception, then we'll mark the instruction in the EX stage. So recall that the way that we are marking, this is kind of simple, that for any interrupt that when that arrives, so we basically, whatever instruction is in that cycle in the MA stage, we will mark it. And for an exception, we'll mark it whenever we see an exception. In whichever stage there is an exception, we'll mark that instruction. So recall that the way that we are trying to do this is to basically ensure precise exceptions. And there are all kinds of state in a program. For example, there are the registers, which are permanent state. There is memory, which the store instruction writes. Then there is a flags register, and then there is the PC. So whether we access all of them, store all of them, or how we manage them will be gradually clear as we keep on describing. But it's important to know that these are all the pieces of state that we have. Alright, so now once an instruction is marked, we have two kinds of instructions in the pipeline. One set of instructions after the marked instruction, and one set of instructions before the marked instruction. Alright, one after and one before. Our job is to ensure that all the instructions after the marked instruction complete, right? And none of the instructions before the marked instruction complete. That's our job to ensure, alright? That everything after it completes and nothing before it completes, right? Completes means either reaches the MA stage or makes a change to the registers or the memory. So the flags register is not a part of this. Alright, so now we go to the next. So now what we do is we wait till a marked instruction reaches the end of the pipeline. After that, we convert all the instructions after the marked instruction which are there in the pipeline to bubbles. So in a sense, they are cancelled. Alright, and we also ensure that all the instructions after the marked instruction are not able to make any permanent changes, right? So basically, if this is the marked instruction, all the instructions after it are sort of converted to bubbles. And once this reaches the end of the pipeline, we can pretty much clean up the pipeline. So this ensures that both the conditions of a precise instruction are met. And the reason being that at least the conditions we have set, that let's assume we mark the instruction in the MA stage. So we wait for these two instructions to get out, and all the other instructions are converted to bubbles. So they have no effect at all. So once the marked instruction reaches the end of the pipeline, the exception unit will load the PC of the interrupt handler. For the exception unit is a special additional unit that we are adding. Alright, so as I said, the program state, the state of a program is its program counter, the set of all the 16 simple RISC registers, the flags register, and memory. Alright. So we assume that in the case of memory, there is no overlap of memory regions between the program and the interrupt handler unless explicitly intended. So let's assume that memory for our program and memory for the interrupt handler is separate. So this is all the state that we are talking about. So we need to ensure that our instruction IK and all the instructions before it in the pipeline update the state, and whatever state we have, the same state is exactly loaded back after the interrupt handler finishes execution. That's our aim. So what is the state again? The PC, registers, flags, and memory. Alright. So let's add a little bit of additional work, but maybe we can have a brief discussion right here, and I'll discuss the logic behind marking. Okay, so let us assume that we have marked our instruction. So basically in the MA stage, we mark the instruction, which means that this instruction and this instruction need to complete. So if we want to exactly start our position in the instruction after the MA stage, what is it that we require? So what we would require is that if we have the PC of the instruction that is there in the MA stage, then and also if just in case this instruction is a branch, so we also have the next PC, right, the branch target, then we can happily cancel all of these instructions, right? It doesn't matter, all these instructions can be cancelled, and next time we'll start from the next PC, which is either this PC plus 4 or the branch target, right? So this ensures that we can recover the program state for the PC. Similarly, no instruction before the RW stage has actually modified the set of registers. So if we don't allow any of these instructions to modify the registers and just allow these two instructions to leave the pipeline, the state of registers at the end, if we have some way of capturing and restoring it, we'll be able to come to the same state as it would have been after executing the instruction, after executing the marked instruction in the MA stage. So this also can be done. Subsequently, what we need to do is that when we return, we need to restore the state of the flags register to the flags that the MA instruction would have seen, or in the case of CMP instruction would have set. So we need to have some way of doing that. We'll find out how. And also in the case of memory, what we need to do is that, so this can be a store instruction. That's the reason we mark this stage, the instruction in this stage, but none of the instructions prior to this would have actually written something to memory. So in any case, they are being invalidated, converted to bubbles. But at least after this point, all our changes to memory would have been done, and no additional changes to memory would be possible. So memory will retain its state because there is no overlap. So no other program is coming and changing the data in the memory regions. So now let's see how to implement all of these things. So memory as such, restoring the memory is not difficult at all because the data remains in memory. So next time when we come back, we can start from exactly the same point. The reason being that so these are all the marked instructions, right? And these are the unmarked instructions. None of the unmarked instructions are actually changing anything in memory. We're not allowing them to. Neither is any other program, including the interrupt handler, changing anything in the memory. So the memory will remain as is. The problem is basically the PC, the registers, and the flags have to be, these three have to be restored to exactly the same state at which we had left, right? So at this instruction in the MA stage, whatever it had left the values of these three instructions with, these three state elements with, we need to come back to exactly the same state, right? Restore the PC, the registers, and the flags as seen or as updated by the instruction in the MA stage, right? Or let's say we are marking some other instructions as seen by the instruction that was marked. So for the PC and register and flags, let's first look at the PC. So let us add a NPC. NPC is next PC field in the instruction packet. Recall that the instruction packet is basically a set of bits that travels along with the instruction in the pipeline. So for taken branches, it will be equal to the branch target. For all other instructions, it will be equal to PC plus 4. Alright, so we will have this in the field. So this will ensure, this will give us some benefits, but I'll talk about it slightly later. So in the NPC, in the EX stage, when we compute the branch target, we populate the NPC field of the instruction packet. And this moves along with the instruction in the pipeline. Depending on the type of the exception, we might want to return to PC or NPC, but that's okay. The exception unit will take care of it. So the exception unit, which is specialized hardware, sets the old PC register to the right return address, right? So which can either be PC or NPC. So depending upon the type of the interrupt or exception, one of these values will be saved in the old PC register, right? So this is an additional register, it's an extra register, it's also called a privileged register because normal programs cannot see it. It's an extra register that we are adding, and the dedicated hardware called the exception unit, what it will do is that it will take the program counter or the next program counter, whichever may be the case depending upon the type of the interrupt or exception, and save it in a new register called old PC, which normal programs cannot access but interrupt handlers can. Alright, so this will ensure that we can come back to exactly the same point at which we had left, right? So basically the instruction that is marked over here, we can either do this instruction or the next one if it's a branch, but at least we'll be able to save this information via this NPC field in the instruction packet and the old PC register, right? Okay, so now let's take a look at spilling and restoring registers, right? So what were the elements of our state? The PC. So we have a way. So, given a marked instruction, so for every marked instruction, we have an NPC field. For every instruction rather. So NPC field either stores the PC plus 4 for this, where PC is the PC of this marked instruction or the branch target. If it's a branch, in any case, it's an X PC. So whenever the marked instruction reaches the end of the pipeline, in a special register, a new register called old PC, either the NPC field is stored, right? And sometimes, depending upon the type of the exception, of course, we want to store the current PC and execute the marked instruction once again. All right. Now let's take a look at registers. So we had three parts of the state that we needed to store. The PC is taken care of. The registers we have to store and restore them, the set of all 16 registers, and the flags register. So flags register is the third. This is the second point. In the case of functions, we used to store registers on the stack, right? So we used to do spilling. In this case, the interrupt handler has to have a separate stack. It can't be the same stack. Because if it's the same stack, it can't be the same area, because we'll have to update the stack pointer. So what will happen to its old, to the old value of the stack pointer? So we cannot overwrite the stack pointer, right? We'll lose its previous value. So let's consider the fact that, we have a program and its stack pointer is pointing somewhere. Then, we don't want to, now let's say we want to save it on the interrupt handler stack, then we'll have to overwrite the value of the stack pointer, right? Such that it points to somewhere else where all the registers can be saved, and this will kill its previous value. So what we do is we add an additional register called old SP to save the stack pointer of the program. So when the marked instruction reaches the end of the pipeline, and that's when all our previous instructions have completed, we save the value of the current stack pointer, which is register 14 in simple RISC, to a new register called old SP, old stack pointer. Then we load a new stack pointer, which is the stack pointer of the interrupt handler, whatever it is, and we spill all the registers there. And in addition to that, we save the old PC and the old SP, of course, in that region. Right, so this has taken care of the storing of the old program counter and the old stack pointer. Now let's take a look at the flags register. So the strange case of the flags register is like this. Let's see. So a simple naive solution will be that we do not allow any instruction after the marked instruction to update the flags register. Then so the thing is, but the problem is that we detect an interrupt or an exception typically towards the middle or end of a clock cycle. By that time, the instruction might have already updated the flags register, right? Or at least the latch, at least the master latch or the master slave flip-flop, if there is one. So this is hard to do, let's not do this, because we'll not know exactly when the flags register is being updated and when it is being restored. So that can be a problem. So let's look at a better solution. So it is true that the flags register is a part of a permanent state, and if let's say this is the marked instruction and all the ones before the marked instruction in the pipeline, all of these need to complete, and none of these can complete before the interrupt handler starts executing. The flags register that this marked instruction would have seen or updated is what needs to come back when we restart the program, right? When the instruction over here starts to execute, this is what it needs to see. So one approach will be that let us add a flags field to the instruction packet. So every instruction will save the updated value of the flags register to the flags field in its instruction packet if it updates it, or the value that it sees when it passes by the EX stage. Alright, so only the CMP instruction updates the flags register, but the rest of the instructions, when they pass by the EX stage, whatever value they see, they will put it in the flags field of the instruction packet, which is a set of bits that it takes down the pipeline. So the exception unit then at the end, when the marked instruction reaches the end of the pipeline, will save the flags field of the marked instruction to the old flags register. So this is a nice way of doing it. So this basically says, go ahead and do whatever you want with the actual flags register. But we'll in addition have a flags field in the instruction packet, which means that whenever any instruction passes by the EX stage, whatever value of flags that it sees or it updates, it carries it along with it. Like in a suitcase, it carries it along with it. When it exits the RW stage, what the exception unit does is that it writes this value to the old flags register, right? Only for the marked instruction. So we'll store the old flags register to a location in the interrupt handler stack. So what are the new registers that we have added? We have added old PC to store the value of the PC that we need to go back to. What are the values? Well, this can be the PC of the marked instruction for some kinds of interrupts, or it can be the next PC for some other kind of interrupts. Then we have old SP. Old SP is the old stack pointer. So the old stack pointer is basically the stack pointer that the marked instruction sees. So this needs to be stored, otherwise how do we update the value of the stack pointer? So this needs to be stored. This is a new instruction we are adding. And also old flags. So this stores the value of the flags register. We essentially have two 1-bit flags, flags.e and flags.gt. But let's treat it as a 32-bit register for the sake of simplicity. So the flags that the marked instruction sees or updates, they will be stored in the old flags register once the marked instruction reaches the end of the pipeline. So these are the three registers that we add. They are not visible to normal programs. They're visible only to special programs like interrupt handlers. So that's the reason we'll call them privileged registers, right? They're privileged, they're special. Alright, so along with privileged registers, right, so what we do is that we add some privileged instructions. So we will add the following new registers to the ISA. So in the ISA, what we can do is that we will also expose the flags register that we have over here to the ISA. So we shall explain in a short while why we need to expose the flags register to the ISA. So, but these are the other privileged registers that we have added: old flags, old PC, and old SP. So, yeah, as I said, this we'll discuss in a short while when you see the assembly code of an interrupt handler. So let us call this as the Z series of privileged instructions, the Z series of privileged instructions. So let's add a few more instructions to operate on these registers, right? The new ones that we have added. So recall that we had discussed the simple disk instruction set in chapter 3, and we had discussed all the registers, but we had not discussed these ones because these are new ones that we're adding now. So in general, what most processor designers do is that they have a normal register set, then they have a special register set for special programs like interrupt handlers. So they will typically have a slightly different encoding. So we need to change the decode unit as well to take care of these instructions. So the first instruction in this class that we want to introduce is the MoveZ instruction, which transfers values between regular registers and special registers. Another instruction we want to introduce is RETZ. So RETZ transfers the value in the old PC privileged register to the current PC, so means we can start executing from there. So the Z series instructions can only be used by the interrupt handler and other and the operating system. So how do we ensure? So the way that we ensure that normal programs cannot access these registers or these instructions is that we use a bit called the CPL bit, and the CPL bit is called the current privilege level bit. For setting permissions, for user programs we set the CPL bit to be 1, and for interrupt handlers and kernel programs we set it to be 0. So what this means is that the user programs will use a certain kind of registers and instruction encoding. So they will not be able to see the special additional registers, old flags, old PC, old SP, or even the flags register for that matter. They can see it implicitly but not explicitly. However, once an interrupt or exception handler comes, the CPL bit will automatically convert from, change from 1 to 0. So then our interrupt handlers and kernel programs will be able to access all the special registers as well as special instructions. Alright, so once then, when the kernel, so kernel I have not defined. So the kernel is, so the operating system code is also known as the operating system program is also known as the kernel. And so it's the same thing, it's just known in our computer science parlance as a kernel. And a kernel is basically a special program to manage other programs, right, which is the job of the operating system. And once we exit the kernel and go back to the user program, the CPL bit will convert from 0 to 1, which means that these special instructions and registers cannot be used. So implementing MoveZ and RETZ, so these opcodes are usable only when CPL is 0. So we augment the OF and RW stages to use these special registers if there is a requirement. And also in this mode we'll see a different view of registers. So let us see just 6 registers. Let us see R0. Let us encode it as 0000. Old PC as 1. Old SP as 2, flags as 3, old flags as 4, and the stack pointer SP as 1110. So this is the same as 14. So it maintains its existing value. But the rest we give them new values. So essentially in a privileged mode we see a different encoding of registers, and these and this encoding also corresponds to different registers, right? Different privileged registers. Alright, so let us look at the assembly code for the interrupt handler, which is to spill the registers. So the first thing that we do, so what is the idea? The idea is that our entire state, right, so memory is taken care of, but the PC, the registers, and the flags, all three of them, have to be stored somewhere in memory, such that later on we can read it from there and we can restore it. Alright, so where will we store it? We'll store it in the stack of the interrupt handler, and from there we can store it somewhere else, but essentially it needs to be stored somewhere in memory. So the first thing that we need to do is that we need to save the stack pointer. Alright, so once the marked instruction reaches the end of the pipeline, so we can sort of clean up the pipeline because the rest of the instructions we have converted to bubbles. So we'll have this circuitry, anything after the marked instruction is all a bubble. So then we load the interrupt handler, and the first thing that the interrupt handler does is that it transfers the value of the current stack pointer to the old SP register. So mind you, this can be done automatically as well. So it can be done in this case via an assembly instruction. So both are possible. In this case, we are doing it via an assembly instruction. Now that this is stored, let us assume that the stack pointer at which we want to store the set of registers in the interrupt handler is 0xFFFC. Let's assume this is the address. So let us load it directly into the SP register, and let's start from there. So now essentially we have loaded a new location, which is the stack pointer of the interrupt handler. So there we will start storing all our registers. So no problem. So we start storing our registers like this. We start storing R0 at SP -4, R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, R11, R12. So we are simply storing the values of all our registers in the stack on the stack of the interrupt handler. And we store, mind you, R13 and R15. We don't store R14 because R14 is a stack pointer itself, so we don't do that. Then we save the stack pointer, the old stack pointer, in old SP. So what we do is that we move it to R0, which is one of the registers that is visible to us in this mode. And then we store the value in R0 to memory, to SP -64. Alright? So after storing the old stack pointer, we now save the flags register, right? So the flags that the marked instruction had seen or updated have been automatically transferred to the old flags register. So this can be transferred to R0, and then R0 can be stored we'll use the regular store instruction. So this can be stored in this particular memory location. And lastly, we will store the old PC. So the old PC, we will store it in this particular memory location. So recall that, just to keep things simple, we have not introduced any additional instructions beyond MoveZ and RedZ. And MoveZ also, we have said it can move data between a special and a normal register, and the rest of the instructions we have kept the same. So once we have done this, we need to update the stack pointer such that the size of the stack, so it's sort of, the stack has increased by 72 bytes. So this is reflected. So we subtract 72 from the stack pointer and use it to update the value of the stack pointer SP. So now that we have saved our entire state, which includes all our registers, the old stack pointer, the old flags, and the old PC, we can start the code of the interrupt handler, because we know that all the state is saved and we just have to restore all of this state to start back again. So for restoring registers, we pretty much work in the reverse fashion. So we update the stack pointer by 72. Then we restore the we restore the old PC. It's not the flags register, it's actually the old PC. So we restore the old PC. So what we do, so recall that the old PC we had saved in this location. So we restore the old PC, right? And so we transfer this to R0, and then we have a MoveZ instruction to do that. And then what we do is that we restore the flags. So sorry, there's another mistake here. We restore the flags. So here what we do is that we take the value in the flags register, and so we take the value in the old flags register, which was actually stored in memory, and we restore it to the flags. So the way that we do it is that we read the value first into one register, and then we do a MoveZ. So we set the flags register with whatever value was previously stored. So recall that that's why, we had exposed the flags register to assembly software such that we can restore its value. Then we sort of walk reverse and restore the value of all the other individual registers starting from R0 to R15. It is just that we leave the stack pointer, so we restore everything but not the stack pointer. We'll do it at the end. So at the end, what we will do is that we will restore the stack pointer. So the stack pointer, where is it stored? Well, the stack pointer is stored at this location, the old SP, right, at minus 64, the contents of SP minus 64. So we will have this instruction over here, which will take the contents of the stack pointer, subtract 64, and then write it to the SP register. So now that we are all done, and our old PC has been loaded, we can execute the retz instruction, which will basically do what? The retz instruction will transfer the old PC to the current PC. It will start execution, and it'll start execution of the original program at the CPL level of 1. All right. So that's what it's going to do. That it'll transfer it, and recall that the old PC we had restored in these lines. So once we call retz, the program counter will be equal to whatever is there in the old PC register. All right. And also the CPL level will be the same as that of user programs, which is 1. So a normal user program can start executing, and its state would have been restored, so it will have no way of knowing that an interrupt had actually come in the middle. It's as simple as that. So to summarize, how did we do it? Well, the way we did it is by actually introducing some special instructions and registers. So in specific, the instructions that we introduced, so let me clean up this slide. In specific, the instructions that we introduced are MoveZ and retz. So MoveZ essentially transfers data between normal and special registers. And retz, what it does is that it essentially returns from an interrupt handler. So the contents of old PC are transferred to the program counter PC, and we start running the user program, and the user program runs with a privilege level of 1. CPL is equal to 1. All right. And these are the 4 additional special registers that we introduce. So why do we introduce special registers? Well, to transfer all the general registers from point A to point B, we need to write assembly code, and assembly code would require registers, and then some of the registers will end up getting overwritten. That's the reason we have to introduce additional registers such that our general purpose registers are not overwritten. So now that we have some understanding of this, let's take a look at our updated pipeline diagram, abridged diagram, of course. So what we have done is that we have, of course, this new marking circuitry which can mark an instruction in any stage. In addition, the PC/NPC/NPC, any one of these values, and the flags, one or both of these values, and the flags field from the instruction packet are going to the exception unit along with the CPL register over here. So the exception unit will control the execution of the interrupt handler. So once the marked instruction reaches the end, we will update the CPL bit, start the interrupt handler or the exception handler depending upon interrupt oblique exception handler. So depending on what kind of interrupt or exception it is, so it will essentially send a command to the fetch unit, and we will start the regular execution, and they will also follow the same pipeline pattern of execution as we have been following. The only additional detail that we need to consider out here is that in our register file we have augmented it. So we have added 4 additional registers: old flags, old PC, old SP, and flags, where this flags and this flags are conceptually the same. And so we just assume that whatever the contents of this flags register and this one here are the same. So this flags register can actually be physically located over here, right? But since it's a register, we have put it in the registered unit. but this and this are the same entity. All right. So this is sort of our entire pipeline processor with the stall logic, the bubble logic, the data hazard and control hazard handling logic, with the forwarding unit, with the exception unit to take care of interrupts and exceptions, which are extremely useful things, because otherwise how would you interact with IO devices? How would you interact with programs that have faults? So an exception unit is required. And we need additional instructions, of course, which our decode unit will take care. And we need some additional registers which are saved in the registered unit, and of course an exception unit with the CPL bit. Alright, so this brings us to an end of the pipelining chapter. So we have now discussed in a fair amount of detail the design of a processor, and we have further optimized it with pipelining. So now this part of the book ends. Subsequently, we'll move to the design of memory systems.